So we're now on to our last unit in statics, which is on the subject of friction, similar to dynamics. So, key points to start off with. Friction is still given by exactly the same formula as it was before. Note the use of the less than sign. Obviously, friction doesn't always have to be at its maximum. At its maximum, still given by exactly the same. Mu is the coefficient, n is the normal. The key phrases which we're looking out for now are limiting equilibrium, or on the point of moving or slipping. Both of those phrases give us the assumption that friction is at its maximum, so then we can use that calculation there, but obviously because it's still statics, it will say that the particle is not accelerating. Watching out for these phrases is really important for when you come to the exam, so that you can tell between whether it's a statics question or a dynamics question, and about friction being at its maximum. The only difference with statics is that because there isn't any movement, you've got to think about which direction would the particle be going in if friction wasn't there. So for example, if you've got a particle on a slope, if nothing else was acting on it, then you'd expect the particle to fall down the slope, so friction must act up. However, if you've got a force which is trying to push the particle up the slope, then friction is likely to be acting down to stop that movement from happening. Okay, here's our first example. So we've got a block of mass 3 kilograms resting on a rough horizontal plane. Immediately we're looking at this word rough and we're thinking we've got friction involved. The coefficient of friction between the block and the plane is 0.4. That's going to be a useful bit of data for us, and we might just want to write it down to remind us. When a horizontal force P is applied, the block remains in equilibrium. Okay, so here's our surface with our block on it with a mass of 3 kilograms. It's going to have a horizontal force P, and naturally in the opposite direction then it's going to have friction. I don't know yet whether it's F max or not, so I'm just going to hold fire on that. Then I've got my normal force going up, and obviously my weight going down. Okay, in part A, it says find the value of P for which the equilibrium is limiting. I'm looking at this phrase here and I'm seeing limiting, so I know it's my F max this time. So if I resolve vertically, I'm going to have n minus 3g is equal to 0, and therefore the normal force is going to be 3 lots of gravity, which is 29.4 newtons. I can then use this to find the value of P for which it's limiting. So when it's limiting, it's going to be exactly static and friction's at its maximum. So resolving to the right, we'll have P minus mu n, so 0.4 lots of 29.4, and because it's static, that's going to be equal to 0. So that gives me a P value of 11.8 newtons, correct to 3 significant figures. Okay, obviously we could do our usual highlighting technique on this, but as it's quite basic with 2 dimensions, it's not necessarily needed this time. Okay, on to part B then. Find the value of F for when P is equal to 8 newtons. So when P was equal to 11.8, that was when friction was at its maximum. So if P is only 8, then friction doesn't need to be this big. Remember that friction only needs to be enough to stop the movement, so it's just going to be 8 newtons in this case to stop the P force. Second example, I've got a box of mass 10 kilograms and it's on an inclined plane. So here's my box of 10 kilograms, and obviously down from it I've got to have a weight. Okay, it's in limiting equilibrium, so that's telling me that I've got friction at its maximum. I'm going to think about which way that goes next. It's a rough plane, well, we already figured out that we had friction. It's inclined at 20 degrees above the horizontal, so this is my horizontal, so it's going to be 20 degrees above it that way. And we've got to find the coefficient of friction between the box and the plane. So resolving this weight here, we're expecting the particle to be rolling down the hill, and therefore friction has got to act upwards. Because it's limiting, we know that that is going to be at its maximum. We'll put normal on here because that's going to help us find out friction itself. So resolving perpendicular first of all, I've got n minus 10g cos 20, and that's got to be equal to 0. Those are my only perpendicular components. Let's say I take them as red. We've got this one and this one. When we look parallel, we're going to have this component and this component. So immediately I can solve that equation and find that n is 92.1 newtons. Now we'll resolve parallel then. We're expecting there to be motion down the slope if there was going to be any, so we'll just resolve that way to make life easier. So we've got 10g sine 20, because that blue bit is the opposite of the angle here, which we know to be 20, minus the maximum friction, so that's mu times 92.1. That's all of our forces and it's statics, so that is equal to 0. So if we rearrange this, we're going to have mu being equal to 10g sine 20 over the normal force of 92.1, giving me my coefficient of 0.364, and again really stressing that that needs to be to 3 significant figures. If you ran that to 0.4, that's really not accurate enough and you won't get the marks in the exam. Okay, this one's a bit of a bizarre question, so we'll just start off by putting on what we know, and then we'll start rereading it to make sure that we've understood it correctly. So we've got a particle of mass 2 kilograms, so we can put that on straight away. That's nothing too confusing. It's on a rough inclined plane, and it's at an angle alpha to the horizontal, so we can add that on. And sine alpha is equal to 5 over 13. It's best if you can get in the habit of recognising this as a Pythag triple, so straight away cos alpha is going to be 12 over 13. It's going to be much easier than trying to do an inverse sine to get alpha and then putting it back into cos. We're also told that the coefficient is a third, so I'll put that with all of my other data. Because I've got a surface, I'm going to have a normal. Right, now onto the trickier bit. We know it's a rough inclined plane, so we know that there's some friction, but we've got to look at this P force acting along the plane, so parallel to the plane this way, which is just sufficient to prevent, firstly, the particle from sliding up, and secondly, the particle from sliding down. So, in both cases, because the only force acting on this so far is downwards, P's obviously got to be acting upwards, otherwise it's definitely going to fall down, and neither of these situations would hold. So P is always going this way for both situations. First of all then, let's have a look at the case of it sliding up the plane. Now if it's about to slide up, as in if friction wasn't there it would slide up, then that's going to tell us friction's got to be acting downwards. So we'll deal with this situation first and then we'll deal with the second one. Okay, so resolving perpendicular. So first we'll go perpendicular. I'm going to go up towards the normal, so the normal minus 2g cos alpha is equal to 0, and I know that cos alpha is 12 over 13, so my normal is equal to 2g times 12 over 13. So either I could leave that as a simplified fraction 24g over 13, or if you prefer you can go for the decimal value of 18.1 newtons. Okay, whether friction's going down or whether it's going up, that normal's not going to change because both of these forces are parallel to the slope, whereas the normal's perpendicular. However, if P was going over this way, for example, and something was changing, such as the friction, then the normal would change. Okay, now we're going to go in the direction of P, and we're expecting it to slide up if friction wasn't there. So P minus mu n for friction, so a third times 18.1, minus also the weight component, 2g sine alpha, has got to be equal to 0. So we can then just rearrange that to make P the subject, which gives us 13.6 newtons, and obviously I've used the fact that I've got sine alpha here, and I know that sine alpha is 5 over 13. Okay, so that's that case. Now we're going to have a look at if it's on the point of sliding down. Okay, so this is the point at which, if friction wasn't there, it would have slidden down the plane. So we're assuming that P's got to be quite small here. It's obviously not fighting this weight component there. And in this case, F is no longer acting down the plane because it's about to slide down anyway. So friction is now acting up. Okay, so I just want to consider the way that that's going now when we resolve parallel. So as I said earlier, the normal staying the same, but now we're going to resolve down the slope going parallel. So down the slope we've got 2g sine alpha, we've got that weight component, we've got p going up the slope, so it's negative, and we've got our mu n going up the slope as well. Okay, and we're solving to find this small force P, which is just enough to stop the particle from sliding down the plane. So it's a minus P in the equation at the moment, so I can add that to get it to the other side. So my expression is now going to become 2g sine alpha minus a third times 18.1. Okay, that gives me a very small P force of 1.51 newtons, which is just enough, along with friction, to stop that particle from falling down.